All right, I think we are up and ready to go. So welcome to everyone out there. Good to see you guys today. I had a question that I'd like to cover with you guys on the confidence intervals for the difference in two sample means. We'll take a look at that, and I'll go over any questions you guys are having on anything else that you might want to talk about. Looking at our learning plan, our calendar here, just be aware that tomorrow I have a quiz planned. You should have gotten a review guide for that that I sent out earlier. It's going to cover hypothesis testing for the difference in two sample proportions and confidence intervals for the difference between two means. So we'll take a look at that tomorrow morning. For now, I have a slide with this question on it for us to look at. So reading this here, researchers investigated how the size of a bowl affects how much ice cream people tend to scoop when they're serving themselves. At an ice cream social, people were randomly given either a 17 or 34-ounce bowl, both large enough that they would not be filled to capacity. They were then invited to scoop as much ice cream as they had liked. Here are the summaries. So looking at this first column, those with the small 17-ounce bowl, 26 people filled an average of 5.07 ounces of ice cream with a standard deviation of 1.84 ounces of ice cream. Let's call that group 1. So X bar 1 is 5.07 ounces. The standard deviation for the sample mean in group 1 is 1.84 ounces. And the sample size for group 1 is 26. For the larger bowl, the 34-ounce bowl, we see 22 people were given a large bowl. They poured an average of 6.58 ounces of ice cream into those bowls with a standard deviation of 2.91 ounces. So we'll call that group 2. Their standard deviation was 2.91 ounces, and the sample size for group 2 was 22. We are asked to create a 90% confidence interval for the differences in the amount of ice cream scooped between the two different bowl sizes, the large and small bowl. All right, so the formula we're going to need, if I write it on the next page, is this. X bar 1 minus X bar 2. That would be the difference in our sample means, plus or minus the margin of error. The margin of error is some t-score to create the confidence interval, whether you want a 90, 95, or 99, those typical confidence interval t-scores, times the square root of the variance, our standard error. This would be S1 squared divided by N1 plus S2 squared divided by N2. Now, before we actually set up the formula, let's talk about what t-score we need. What t-score we need to make this overall confidence interval. I need a t-score that captures 90% of the distribution. So we take a sample, call it X bar, and I want a 90% chance based off my margin of error. I want my margin of error to have a 90% chance when I add and subtract it of calculating or capturing, of capturing the true population mean. Well, if I have 90% in the middle, that leaves me 5% in either tail. So I need to come up with a way to find the t-score where 95% of the distribution is to the left. Now, if you remember anything about t-scores, I need to first know how many degrees of freedom are in my sample. Degrees of freedom is one less than the sample size. So for group 1, I have 26 in the sample, so I'd have 25 degrees of freedom. For group 2, I have 22 in the sample size, so I'd have 21 degrees of freedom. So therefore, my total degrees of freedom for the two samples put together would be 25 plus 21, or 46 degrees of freedom is each of the two sample sizes added together minus 2 for the total degrees of freedom. I have two groups, each with n minus 1 degrees of freedom, so altogether that'd be minus 2 for our degrees of freedom. Going back here, it's 25 plus 21, making 46 degrees of freedom. If I look at my t-table, a 90% confidence interval is in the second left-handed column. But where is 46? Well, I can get pretty close with about 1.679, and that would be fine. You could certainly use 1.679 because 45 degrees of freedom is pretty close to the R value of 46 degrees of freedom. Or if you want a more accurate t-score, I can open up a Google Sheet and type in E dot equals T dot INV. And it's going to give me the t-score for a specific distribution. There was 95% of the distribution to the left of the t-score for 46 degrees of freedom. I see about, once Sheets calculates that here, about 1.678, 1.679. So yeah, pretty much the same as what we had on the t-table that we saw here, 1.679. All right, we're going to get this set up here in a second, but let me pause. Were there any questions before I go any further? All right, let's keep going. I need the difference in our two sample means, so 5.07 minus 6.58. Plus or minus the margin of error with our t-score of 1.679. Times our standard error of 1.84 squared divided by 26. Okay, the same thing for group 2. 2.91 squared divided by 22. All right, the rest is left up to Desmos. Let's first find the estimate for our difference between these two means from the sample, 5.07 minus 6.58. negative 1.51. Now, I called group 1 and group 2 the small and large bowl sizes, but you could have just have easily switched those around. You would have just gotten the exact opposite. Instead of negative 1.51, you would have gotten positive 1.51. This negative 1.51 shows that there's 1.51 ounces less ice cream in the small. If you switch those, you would have gotten 1.51 ounces more ice cream in the large bowl. Just a different interpretation, but it's roughly the same thing. Okay, next, let's go ahead and get this margin of error calculation figured out. 1.679 times the square root of 1.84 squared over 26 plus 2.91 squared over 22. $1.205. Which means that our estimate in the difference between these two bowls of ice cream of 1.51 ounces is no more than 1.205 ounces from the actual overall population difference for the amount of ice cream in the bowls in question. So let's go ahead and get this total confidence interval built. Negative 1.51 minus the margin of error. Negative 2.715. And then plus the margin of error. Negative 0.305. And that is in ounces. For our interpretation, we are 90% confident that the small bowls of ice cream contain between 2.715 ounces to 0.305 ounces less ice cream than the large bowls. Now, because this confidence interval is strictly negative, because 0 is not in this confidence interval, our data shows that there is a difference in the amount of ice cream between the large and small bowls. People are generally putting less ice cream in the smaller bowl than in the larger bowl. So the data shows evidence that people are putting less ice cream in the smaller bowl than in the larger bowl. All right, kind of wrapping that up there. Questions on this confidence interval? Okay. Since there's no questions, if anybody had a problem or two off of the review that I sent out or the S22 practice problems, I'd be happy to go over any of those. Just go ahead and speak up and we can go over any and all questions people are having.
I'd like to go over number one.
Number one here, okay? So looking at number one, it says that during the 2017-18 NBA season, Steph Curry led the league in free throw percentage by making 278 out of 302 free throws. So let's get that copied down. So proportion one for Steph Curry is 278 out of 302, which as a decimal is 0.9205. Okay, so for the misses, well, if you made 278, he would have missed 24. Should be everything else. 0.0795. Curry also took 302 free throw attempts for our sample size. Going back to here, Chris Paul finished in second for the league by making 203 out of 203 out of 221. So for group two, .203 out of 221 is 0.9186. If he made 203, he would have missed 18 out of his 221. Which is 0.0814. And we have a sample size of 221 for Chris Paul. All right, so let's check some conditions here. All right, for two proportions, hypothesis testing and confidence intervals, we're looking at these conditions here in the second row, second column from the right on your formula sheet. Was this a random sample? Well, we're only looking at 1 year. It might be might be better suited for us to look at a couple of years, a collection of years, their NBA totals altogether, but we'll go ahead and assume that they just picked one random year, perhaps. I think the 200 or so free throw attempts are less than 10% of all free throws shot by these two players. So that checks out. Now I have to have at least 10 successes and failures for each of these two players. So going back to our data here, I can see that I have at least 10 in all four of those values. So our conditions are satisfied. Next in our hypothesis testing is to define both the null and alternatives. We're testing to see if Steph Curry is a better free throw shooter than Chris Paul. So therefore, his proportion of free throws made altogether would be greater than Chris Paul's for P2. So let's assume that, to start, there is no difference between Chris Paul and Steph Curry's free throw percentage. If you want to go ahead and define a rejection region, that would be fine. This should be a one-tailed test. And did it give us a significance level? Yeah, 5%. So 95% to the left, 5% to the right. Our cutoff z-score on the formula sheet, since this is a one-tailed test, I see 1.645. If we can calculate a z-score that's more extreme, greater than 1.645, we have significant results, and our evidence would show that Steph Curry is a better free throw shooter than Chris Paul. Your formula for this, for our test statistic, is the difference in the two proportions, P1 minus P2, divided by the variance, P1 times Q1 over N1, plus P2 times Q2 divided by N2. So if I get this typed into Desmos, 0.9205 minus 0.9186. Divided by the square root of 0.9205 times 0.0795 divided by 302 free throws plus 0.9186 times 0.0814 out of 221 free throws for Chris Paul. I get a z-score of approximately 0.08 if I round to the nearest hundredth. Let me stop here. Questions so far? Okay, so compare these two z-scores. What should our decision be? Do we reject or fail to reject the null hypothesis? If we reject, do we have a z-score that's more extreme than 1.645? I think we'd have to fail to reject the null hypothesis. We lack evidence to suggest that overall Steph Curry is a better free throw shooter than Chris Paul. Going back to here, our z-score of 0.08 was to the left of 1.645. It's not more extreme. Your last step in a hypothesis test, very important, is to calculate the probability value for your sample. So what is the chance of a z-score being greater than, more extreme than our z-score from the sample of 0.08. Well, if I go back to my z-table, once this loads, .08 is 0.5319 to the left. If I want to the right, we'll do 1 minus 0.5319. Which is about 0.4681. So if it was actually true, I'm sorry, the p-value defined to be the probability of our sample or sample more extreme if the null hypothesis were true. So the null hypothesis is that these two free throw shooters are the same. If it was actually true that there was no difference in Steph Curry and Chris Paul's ability to make a free throw, we would see a sample such as ours 46% of the time. Well, that's not rare enough for us to assume that any one is better than the other. So we fail to reject the null hypothesis. We lacked evidence that Curry's better than Chris Paul. Hope that helped. Are there any other questions off here? We could look at more problems on the review guide or anything off the practice problems from standard 22. Okay, hearing nothing, I guess we'll call it a day here. If you do have more questions, feel free to reach out. I've got plenty of time to help you guys if you do have any problems. We can chat via email or set up a Google Hangout call and go over any questions you have. Tomorrow, we'll do the quiz. So same time, same place tomorrow. Have a great rest of your day.
I do have one question,
Please,
Mr. Hansen. How do we do reassessments?
Reassessments, anything you want to reassess, just let me know. And I can get an assessment ready and we'll put a time together to do another Hangout call when you have time available that you want to reassess on.
Okay, and I still need to take our previous test because I could not figure out how to work Zoom at that time.
Okay.
So could we just do both those in the same time period?
Oh yeah. I've had a couple students knock out a couple quizzes and reassessments in one call, and that's fine.
Okay.
Yep. Just let me know what you're thinking, what time you have available, and we'll go from there. Okay.
Okie dokie. Thank you.
No problem. Thank you. All right, guys. Have a good rest of your day.